At the limits of reality, numbers, both huge and tiny, abound in science, and for obvious reasons. The universe is incredibly large, and the particles of which it is ultimately composed are fantastically small. We can quickly end up going well past a trillion if we start to count the numbers of very small things in nature, such as atoms, or measure on a cosmic scale with units that seem reasonable for everyday purposes. For instance, the meter is a sensible unit in the human world, but not so much when we start talking about interstellar distances. Even the nearest star to the Sun, Proxima Centauri, lies about 40,000 trillion meters away. The routine appearance of very large and very small numbers in science is why scientific notation is commonly used. In scientific notation, also known as standard form or index form, 40,000 trillion is written completely as 4 times 10 to 16. This makes it easy to see at a glance how many zeros come after the 4. Another way to make the numbers worth dealing with more manageable is to use bigger units. That's why astronomers often talk about distances in terms of light years or parsecs. One light year is the distance traveled by light moving at 300 million meters per second in 1 year. It equals about 9.46 trillion kilometers, so that the distance to Proxima comes out to be 4.24 light years. A parsec is the distance at which the average diameter of Earth's orbit around the Sun supports an angle of 1 over 3600 of a degree, known as 1 arcsecond. It works out to be 3.26 light years. Proxima is 1.30 parsecs away, and the center of the Milky Way galaxy a little over 8,000 parsecs from Earth. Even the parsec, though, starts to seem small once we move beyond our own galaxy and deep into the intergalactic void. Then astronomers turn to the kiloparsec, the megaparsec, and finally the gigaparsec, a billion parsec. The, di- the distance across the entire observable universe is about 28.5 gigaparsecs, or 8.8 times 10 to 23 kilometers. As we saw in the first chapter, numbers of this magnitude are nothing new in science. Archimedes' cosmic count of centigrads was around 8 times 10 to 63 in modern notation. Fortunately for us, the universe isn't actually packed full of sand. Nevertheless, there are some other extremely big numbers in science that apply to real situations, or at least our attempts to estimate them. Back in 1811, Italian scientist Amedeo Avogadro proposed, proposed that the volume of gas at given temperature and pressure is proportional to the number of molecules within it regardless of the actual gas involved. This would mean that equal volumes of different gases, for example, oxygen and carbon dioxide, under the same conditions, contained the same number of molecules. Although Avogadro believed in the existence of atoms and molecules and drew a distinction between them. He no way of knowing their size. They finally reasonably accurate measurements of what became known as Avogadro constant were made in the early 1900s from experiments carried out by French physicist Jean Perrin. Today, the value of Avogadro constant is known accurately to be is defined to be the number of constituent particles which may be molecules or atoms or even ions in a quantity of a substance called a mole. 1 mole is the molecular weight of a substance in grams. So for instance, 31.9988 grams of oxygen and 44.0095 grams of carbon dioxide under the same conditions, but contain 6.022140776 times 10 to 23 molecules. But if we the standards in this this number 600 billion trillion is immense. In fact, it's the largest physical constant with which scientists deal on a routine basis. It also gives a feel for the minuscule nature of atoms and molecules. 1 mole of water weighs just 18 grams and occupies only a few drops, yet it contains 600 billion trillion water molecules. A much big number was named after another famous scientist, Sir Arthur Eddington, in his book The Mathematical Theory of Relativity, published in 1923. Eddington wrote, "I believe there are proton, protons in the universe and the same number of electrons. What outrageous about this isn't the size of the number. After all, the number of protons and electrons across the whole universe is bound to be humongous, but the extraordinary precision with which it was stated. Had Eddington simply declared the total number of protons to be about 1.57 times 10 to 5 times to 10 to 79, or about 15.7 million trillion, it wouldn't have created much of a stir. However, he claimed to have figured out the, the value down to the last particle. By the time Eddington became interested in large cosmic numbers, he was already a world-renowned astrophysicist. In 1919, he led an expedition to observe a total solar eclipse in South Africa, which confirmed one of the key predictions of Einstein's general theory of relativity, that the path of light from a star will be bent when it passes near a massive object, in this case, the Sun. He was also a pioneer investigator of stellar physics and the first to propose in 1920 the stars generate their heat and light by the process of nuclear fusion. During the 1920s, Eddington began to obsess more and more about building a grand theory that would unite relativity, quantum mechanics, cosmology, and gravitation. Although he started out conventionally enough, his work soon began to take on both elements of numerology and aesthetics. He wasn't alone in this almost mystical fascination with what became known eventually as the last numbers hypothesis. In 1919, German mathematician Hermann Weyl started the ball rolling by noting that the ratios of some basic distances and forces in nature were both very large and very similar. For instance, the electric force between a proton and an electron is about 10 to 40 times as big as the gravitational force between them. This same factor of 10 to 4, 10 to the 40 cropped up when Weyl divided the radius of the universe as it was then estimated to be by what's called the classical electron radius. As Eddington delved into these same kinds of relationships, they linked the submicroscopic world with the microscopic. He became especially intrigued by an enigmatic factor in nature known as the fine structure constant. This constant crops up in all kinds of places in atomic and nuclear physics. One of the things it does to calibrate the strength of electromagnetic force between elementary charged particles such as electrons. Other physicists right up to the present have been struck by its pivotal role in cosmic affairs at different scales. Wolfgang Pauli had a lifelong fascination with the number, once commenting, "When I die, my first question to the devil will be, what is the meaning of the fine structure constant?" Richard Feynman referred to it bluntly as one of the greatest damn mysteries of physics. At the time Eddington first turned his attention to the fine structure constant, its value wasn't known from experiment to any greater accuracy. It was thought to be about 1 over 138, 1 over 136 in a series of convoluted shapes. Eddington claimed to have proved theoretically that the value was exactly 1 over 138, and because of this, his reasoning led him to believe the number of protons in the universe was 136 times 2 to the 256. This is the infamous Eddington number, which he brought out in full in his book 1923 book and repeated again in the public lecture he gave in 1938 at Trinity College, Cambridge. Unfortunately, later experiments led to the value of the fine structure constant being adjusted downwards, putting it closer to 1 to the 137. In fact, it's known to be 1 over 137.035999084. That experimental readjustment didn't flash Eddington. He simply tweaked his theory so that it produced 1 over 137 exactly. But not surprisingly, no one else was persuaded by such a convenient fudging of the issue. Other scientists lost faith in his large number reasoning, and the satirical magazine Punch captured the mood by dubbing him Sir Arthur adding one. Eddington's number turned out to be a fiction, but it does retain one distinction: it is the biggest specific number, not an estimate or approximation, that ever been claimed to have a bearing on the physical world. As mentioned, when lots of little bits make up relatively gigantic things, big numbers are bound to crop up. The cells that comprise our bodies are microscopic in size. A few tens of trillions of them are needed to make up an average human being. What you're using to assimilate these ideas at the moment is a brain that contains about 68, uh, 86 billion neurons or nerve cells. That's the number arrived at by the time of researchers at the University of Rio de Janeiro in 2009. Because each neuron is linked to many other neurons, the total number of connections in the brain is much larger than 86 billion. A figure of 100 trillion is in the right ballpark. Every second, about 7, 750,000 gallons of water flows over Niagara Falls, the great majority of it at the Horseshoe Falls. That amounts to 2.7 billion gallons per hour, 23.7 trillion gallons per year, or 1.9 times 10 to 15 gallons over an average human lifetime. Given that there are about 1.27 times 10 to 26 molecules in a gallon of water, this means that in the lifetime of a person who lives 80 years, roughly 2.4 times 10 to 41 water molecules will have dropped over the falls. At its current rate of flow, it would take about 13.8 million years of all the water on Earth to go over Niagara. A useful way to grasp these kinds of numbers, millions, billions, trillions, and so on, is to think of the cubes of dots. Start off with a small number like 100, which might be how many people are at a modest-sized wedding reception. Imagine a cube that has 100 dots of each edge. Then it will have 100 times 100 dots per face, or 100 times 100 times 100, or 1 million dots together through its volume. Cults, a million people sometimes come together, for instance, at religious gatherings such as the Hajj, the annual Islamic pilgrimage to Mecca. Somewhere between 500,000 and 1 million descended on the Woodstock Festival in 1969, so we can guess the size of a million to some extent through pictures and in our mind's eyes. Moving on, a cube that has 1,000 dots on each edge will contain a total of a billion dots. A cube that has 100,000 dots along the edge, one for each person, is a big packed stadium contain 1 to 10 to 5 times 10 to 5 times 10 to 5 equals 10 to 15 or 1,000 trillion dots, which is roughly as many as the numbers then which is roughly as many as the number of connections between neurons in 10 human brains. To celebrate his first to celebrate his first billion seconds of life, reached on 1 March 2020 during his 31st year. Dutch design the Dutch Dutch design engineer Daniel De Bruin invented a machine that takes over than that takes more than a Google number of years to complete one rotation. Plenty of devices, from cars to washing machines, use reduction derivatives, a series of connected gears, to decrease the speed and increase the torque produced by your motor. De Bruyn simply took this idea to an extreme by connecting 100 gears each with a reduction ratio of 10 to 1, so that for every 10 rotations of one gear, the next turns only once. The final gear in the chain rotates a goggle 10 to 100 times more slowly than the first. Since the first since the first takes about 4 seconds to complete one revolution, the 100th gear has a rotation period of about 1 times 10 to 100 seconds. This roughly 1.3 times 10 to 93 years of 1.3 times 10 to 93 years, or about 100 billion trillion times the current age of the universe. De Bruin has already shared on the internet videos of his machine running of a full hour, and has considered setting up a live stream for those who enjoy this action. Slow and predictable. Just don't expect much in the way of movement from the majority of the gear wheels. The motion will be undetectable even to the most sensitive instruments on Earth. As for the total energy required to turn the last gear around once, it will be far greater than all the energy in the universe combined. Science is, isn't the only aspect of life that can spawn gigantic numbers. Sometimes, when the country's currency is hit by hyperinflation, almost everyone in the nation becomes a multi-trillionaire virtually overnight, and yet may still be more or less penniless. It happened in the Weimar Republic in the early 1920s, when Germany was saddled with a massive debt from the cost of the First World War and subsequent reparations that they agreed to pay. By November 1923, the US dollar would have brought but by November 1923, the US dollar would have brought to you 4.2 trillion German marks, and the currency was so worthless the banknotes were being used as wallpaper or kindling, and workers took suitcases and wheelbarrows to work to collect their wages. The following July, a total of 1.26 trillion marks were in circulation. Just after the Second World War, Hungary suffered a similar financial crisis when its inflation rate reached 41.9 quintillion%, the highest on the record. This prompted the issue of banknotes of ridiculously large denomination, culminating in 1946 Sasmilo Pingo. Sasmilo B stands for 100 million. So, with one of these in your pocket, you'd have been the proud owner of 100 quintillion pengos, enough to buy, well, probably not very much. To put, to put in context, assuming a single pengo note measures 5 centimeters of by 10 centimeters, 100 quintillion of them would have been enough to completely cover the Earth's surface 20,000 2,000 Rogers deep. Things got so bad in Hungary that it was decided to introduce an entirely new currency. One, uh, on 1 August 1946, the foreign replaced the pengo. To be more accurate, one foreign replaced 4,000 octillion, or 1 times 10 to 29 pengos. At a stroke, the total amount of pengos of the total amount of pengo notes in circulation was reduced in value to less than 1,000 of a single unit of the new currency. Still on the subject of finance, the richest person on earth is Jeff Bezos, founder of Amazon, with an estimated wealth of 190 billion dollars. But that's peanuts compared to the largest ever lawsuit for undecillion to the 2 trillion dollars filed in 11 April 2014 by Manhattan resident Anton Purisima after claims that he was bitten by rabies-infected dog on New York City bus. In a rambling 22-page handwritten complaint, accompanied by a photo of an unreasonably outsized bandage around his middle finger, Purishima Shield NYC Transit LaGuardia Airport, Auburn Plain, where he insisted he was routinely overcharged for coffee, Hoboken University Medical Center, and hundreds of others for vastly more money than there is on the planet. Fortunately for the defendants and the world's monetary supply, the judge dismissed the lawsuit, stating the court, after reviewing plaintiff's complaint, finds that it lacks any arguable basis in law of in fact. As you can imagine, some of the biggest numbers of relevance to physical reality come about what we try to count how many of the smallest things ever conceived by science would fit into the largest thing, of which we know the universe itself. But it's not immediately obvious what are the values of these two extremes in size. The entire universe is thought to have sprung into existence in an event known as the Big Bang some 13.8 billion years ago. Ever since then, the cosmic contents have been flying apart like debris from a colossal explosion, scattered further and further asunder on the spreading surface of four-dimensional space-time. The overall nature of the universe, including its shape and whether it's infinite or infinite in size, remains uncertain. We can get information only from the part we can see, the portion of the universe which light has had a, a chance to reach us since the Big Bang. This is the so-called observable universe, which is believed to have a diameter about 93 billion light years, or 8.8 times 10 to 26 meters. If we assume that it's spherical in shape, then its volume comes out to be roughly 4.1280 cubic meters. At the other hand, at the other end of the scale in the world of atoms, subatomic particles, and quantum mechanics, a hydrogen atom, for instance, measures just 1/10 billion of a meter across. That's 1 divided by 10 billion over 1 over 10 to 10, which we can write as 10 to the minus 10 meters, the minus sign indicating the 1 over of reciprocal. The hydrogen nucleus, a single proton, is far smaller, with a diameter of just 2 times 10 to the minus 14 meters and a volume of 4 times 2 for 10 to minus 42 cubic meters. In terms of volume, then the observable universe is 1 to the 122 times bigger than a proton. But a proton is a long way from being the smallest thing in nature. Inside the proton are even tinier particles called quarks, and much smaller than any fundamental piece of matter is something known as the Planck blank. Physics hypothesis that few a sufficiently high magnification, the graininess of spacetime itself would become evident. Normally, we think of spacetime as being a smooth and continuous backdrop against which the drama of matter and energy plays out, but at short enough lengths and times. This continuity this continuity is thought to break down and the quantum nature of space and time become apparent, named after German theoretical physicist Max Planck, who first proposed it in 1899. The Planck length is about 1.6 times 10 to minus 35 meters. A sphere with the diameter would have a volume about 2 times 10 to minus 105 cubic meters, dividing the current volume of the observable universe 4 times 10 to 80 cubic meters. By this fantastically tiny number tells us how many times the smallest physically meaning volume will fit into the largest actual volume of which we know. The answer, about 2 times 10 to 185, written out in full with apologies to proof reader. It is 206 gintillion. We don't know how much bigger the entire universe is than the observable universe. One possibility is that the universe is, and always has been, infinite in size. Even if it's finite, the path we can see is likely to be only a smaller fraction of the whole. Much depends on what happened during an extraordinary rapid early phase of cosmic revolution, now an inflation, which began about 10 to minus 37 seconds after the Big Bang. Low estimates suggest that the whole universe has at least 250 times the volume of what's currently observable. Higher estimates put in excess of 10 to 70 times as big. In any event, the ratio of the volume of the universe in its entirely the volume spanned by a single Planck length must be far greater than already gigantic number we wrote in full above. Colossal numbers also arise when we start to think about the limits of computation in the real world. Here we're talking not about what, in theory, is possible to compute given endless amounts of time and storage space. More on this later, but instead of the practical limits imposed by the laws of physics. One of these is known as Bremermann's limit, after the German-American mathematician and biophysicist Hans Joachim Bremermann. It's based on two fundamental principles. The first is the equivalence of the mass and energy as specified by Einstein's famous relation E = mc squared, where c is the speed of light. The second is Heisenberg's uncertainty principle, which expresses the precision with which certain pairs of quantities such as energy and time, and mass and momentum can be known. Bremermann's limit is the maximum rate at which data can be processed by any isolated material system. It's equal to c squared over h, where h is Planck's constant, and come out to be about 1.36 times 10 to 50 bits per second per kilogram. We're not used to seeing processing capacity expressed in this way. Normally, we read about how many bits per second a chip or a computer as a whole can process. That's because Bremermann's limit far exceeds the processing rate of any humans have ever made or are likely to make in the foreseeable future. It's, however, of interest in the design of cryptographic systems that are secure against brute force, such as that try to crack secret codes and passwords by running through all possible combinations. Imagine a computer as massive as the Earth that can work at Bremermann's limit. It would be capable of roughly 10 to 75 computations every second. At this rate, it could break a typical 128-bit cryptographic key in less than 10 to minus 36 seconds, and a 256-bit bit key in about 2 minutes. However, cracking a 512-bit key, even for a planet-sized behemoth working at the computational speed limit, will take an impossibly long 10 to 72 years. Another and related extreme limit on what's computationally possible in nature is the Bekenstein-born named after Mexican-born Israeli-American physicist Jacob Bekenstein, who came up with the idea in the early 1680s. It refers to the maximum amount of information that can be contained within a given volume of space. In defining his bound, Bekenstein had in mind the most extreme objects in the universe, black holes. Specifically, he was looking into the problem of what happens if something falls into a black hole. It used to be thought that once having entered a black hole, nothing could escape, nothing could ever escape. However, Stephen Hawking proposed a way that information might be extracted, leading to the possibility of using a black hole as the most extreme data storage or computational device with a storage density equal to the Bekenstein bound. MIT engineer and physicist Seth Lloyd calculated that the ultimate laptop, formed by compressing a kilogram of matter without a black hole 3 times 10 to minus 27 meters across, would be able to perform 5 times 10 to 50 operations per second. On the downside, being a submicroscopic black hole, it would evaporate in a flash of gamma rays, gamma, gamma rays due to Hawking radiation in about a 10 million trillion of a second, which is make it less than ideal for everyday use. At the other end of the scale, Lloyd figured if it all the matter in the observable universe were turned into a black hole computer, it would be capable of 10 to 90 operations per second and have a lifetime of 2.8 times 10 to 139 seconds before Hawking radiation caused it to evaporate. In that time, it would be able to perform 2.8 times 10 to 229 operations. Though given that the computer would be coextensive with all physical reality, it's hard to know what the purpose and nature of those operations would be. In the world of science fiction, anything is possible. Every being pushed out of an angle of one spaceship and being rescued moments later by another spaceship that just happens to be passing by. In the Hitchhiker's Guide to the Galaxy, Douglas Adams gives the dots of his characters out to death and thought perfect enjoying such a monumental streak of luck. After being ejected from a foregone spacecraft to to the to the 260 199 to 1 against. As it happens, they are rescued by the heart of gold powered by an infinite improbability drive. It might not seem possible that there could be numbers even bigger than this that describe aspects of the real world in which we live, but there are some that are ridiculously larger than all of those we've looked at so far, and as in Adam's book, they involve probability. These books refer to what are known as Poincare recurrence times, and they're spectacularly stupendous in size. A Poincare recurrence time, named after French mathematician and physicist Henri Poincaré, is the time taken for a system such as a collection of moving particles to return to exactly the same state in which it started. Naturally, the bigger and more complex the system, the more possible states it can have and the longer it will take to come back purely by chance to its initial condition. Canadian physicist Don Page has calculated Poincare recurrence times for the entire universe under a variety of different starting conditions, depending on the model used to describe the earliest moments of the universe. Page came up with a range of recurrence times extending all the way up to this many years. Nothing we've talked about so far comes anywhere near this in size. In fact, it's the larger number even to be calculated and published in academic journal by scientists, though not by a mathematician. It's also the first time in this book we've seen something represented in this way in the form of a stack of exponents. 10 to the 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 1.1. For convenience, we can also write it using carats of circumflex ascents, as we'll be seeing a lot more. We will be seeing a lot more of this type of number, a repeated exponential, later on. For now, it's worth pausing a moment to understand what it means. Ignore the 1.1 and think about 10 to the 10 to the 10 to the 10 to the 10. Evaluating this from right to left, in other words, going down to the powers. 10 to the 10 is 10, or 1 followed by 10 billion zeros. 10 to the 10 to the 10 to the 10 is 10 to the power of 1 followed by 1 billion zeros, and finally 10 to the 10 to the 10 to the 10 to the 10 is 10 raised to the power of 10 to the 1 followed by 10 billion zeros. This might seem a seriously impressive number that is just a baby step along the road, the biggest ones we can name, define, or contemplate. From now on, we must start to leave behind the physical world and enter the domain of mathematics, where the mind is unshackled for limitations of matter, energy, space, and time.